Hi everyone, my name is Alan Davis. I'm a graduate student at Yale, and my work has been on assessing the information content of spectra using PCA. Our main goal is to figure out how much is stellar activity affecting our ability to do radio velocity work. As most of you probably know, stellar activity, or RV jitter from spots and faculae and plage, can hinder our ability to find small planets. So the technique that we've been using is to generate models using the SOAP 2.0 model, which Xavier talked about in an earlier talk. And we create a series of time series spectra for stars that have been perturbed by a spot or a plage or a planet. Then we run a statistical technique called principal component analysis on these spectra, and we just look at what we get. So just in this figure, you can see that spots and plage have different signatures in terms of their principal component scores than planets. So already this is telling us that the spectra behave differently. But perhaps the most important result that we see so far is that under different observational conditions, particularly different signal to noises, different resolutions, we're able to recover a different amount of information in the spectra depending on what we're looking at. So in this figure, I'm showing you the number of significant principal components, with the darker colors being you're detecting more significant principal components. And this figure here is for a spot on a star. And you can see that there are at least 4 different principal components that are detectable depending on the amount of signal to noise and resolution you have. And the important takeaway point here is that high resolution is going to make it easier to access the information that is telling us that activity is causing RV jitter. And this isn't immediately obvious because people have thought that for a long time, as soon as you fully resolve the spectral lines of the stars, you don't need higher resolution. But in fact, this is giving you more information. So I'd love to hear your thoughts on this, so come find my poster. Thanks.
Okay. Good afternoon, everybody. Okay. I'm Matteo Pinamonti. I'm a second-year PhD student at the University of Trieste. And my work is, I can see the slide. Okay. My work is about searching for planetary signals in Doppler time series, in particular a performance evaluation of different tools for periodogram analysis. That is because if you're interested in study planetary systems around low-mass stars, you really need the best possible tools available, because low-mass stars are really bad for stellar activity and a lot of reasons. And the point is that first algorithm that you use to identify a signal in a radial velocity time series are usually the periodograms, which really have never been tested on a statistical meaningful sample in the literature before. So what we did do is to analyze some synthetic catalogs of several thousands of synthetic time series to study the difference efficiency of these 3 algorithms, which are the generalized Lomb-Skargol, which is the standard tool everybody uses, the new Bayesian version of the GLS, proposed last year by the group of Mortier, and the multiple algorithm, the frequency decomposer, which is a multi-frequency periodogram algorithm. Okay, so the point to have such a large sample of time series analyzed that you can quantify all the effect that no one has ever. I don't know if you can see the plot, but it's not just important because you can quantify like the dependence. Okay, and 2 minutes are really short. So the point is that you have a really good agreement on correct identification of real planetary system, and if you find a false positives, the other arguments will disagree. And my poster is number 37. I hope I've confused you, so you can ask me questions. See you later.
Which one's the next one?
This is for pointing, and this is
Only pointing, and then it's changing the slide.
Oh, okay. Go for it. Hi, my name is Kira Wright, and I'm a first-year grad student at University of Florida.
And I'm currently working on characterizing solar-type stars from the radial velocity survey called MARVELS. And I'm focused on determining the effective temperature, metallicity, and the surface gravity of the targets in the survey. And this is important because these parameters can have a big impact on the planets that form around the stars and the ones that we end up detecting, as well as if you're interested in doing transmission spectra, you need to understand the stellar spectra. Yeah, and for doing transmission spectroscopy, you want to understand the stellar spectra really well. So and that's what I'm interested in. So next slide. So the method that I use is I first, to determine what the parameters are, I generate a coarse grid of models from the Phoenix synthetic spectra. And I make some corrections for, of course, like telescope resolution, stellar rotation, things like that. And then I interpolate between those models to create a very fine grid, depending on what those parameters are. And then I compare that fine grid of models to the observed data to try and find the best match. And then, of course, that will tell me what the best parameters are. And so what I have right here are, of course, my results for 3 of the 8 stars that I've figured this out for so far, in a messy kind of table instead of a nice convenient scatter plot like I should have done. And but the takeaway from this is that my results, so right as me in all these, is pretty close to the published high resolution results. My effective temperature RMS is like 57 Kelvin. My metallicity is like 0.04 and log G is 0.1. So they're pretty great. And I think it's going to be a good method for determining the stellar parameters. And if you want to learn more about this, I don't have a poster. You're just going to have to find me and ask me questions. Thank you.
Hello. Okay, hi everyone. My name's Richard Hall. I'm a first-year PhD student at the University of Cambridge, working with Didier Colos. And the title of my poster is Measuring the Effective Pixel Positions for the HARPS 3 CCD. Now we know from instruments like HARPS South and HARPS North that RVs are currently limited to about 1 meters per second. But if we want to find Earth-mass planets orbiting Sun-like stars, we need to have maybe an order of magnitude higher precision, so about 10 centimeters per second. HARPS 3 is a future next-generation instrument that's hopefully going to achieve that. We're going to have a handful of selected stars. We're going to observe each one every night for 10 years. And this will help us measure and correct for any stellar noise. However, at some point, we're going to actually encounter the errors in the silicon structure of the CCD itself. So at Cambridge, we're going to build, or we are building, an experiment to detect and measure these defects in the silicon, which will then help us to achieve 10 centimeters per second resolution. Next slide, please. So effectively, we just have a couple of lasers. I'll just give a really simple overview. A couple of lasers shine onto our CCD, and where they overlap, we generate this nice uniform intensity pattern. We can precisely control this pattern. We can modulate the frequency, the periodicity, the intensity, and we modulate this pattern over a wide parameter space, and we measure the CCD's reaction to this perfect pattern, and eventually where the CCD fails to recreate this perfect intensity pattern, that's where the defects in the CCD are, and this should help to reveal any difference in pixel sizes or things like that. So I'm poster 19, and thank you.
Hi, my name is Sarah Milholland. I just finished my first year at UC Santa Cruz, but shortly after this workshop, I'll be transferring to Yale University. So a recent theory of in situ formation of hot Jupiters by Batygin et al. 2016 suggests that if some hot Jupiters can form in situ, they should be accompanied by nearby super-Earths whose orbits might be highly inclined with respect to the hot Jupiter's orbit. Therefore, searching for non-transiting hot Jupiters in systems with transiting super-Earths offers a direct test of in situ formation theory. We recently published a paper that proposed a new technique for detecting systems of this type. We aim to detect 2 different measurements. The first is an optical reflected light phase curve for the non-transiting hot Jupiter, which has been detected for many transiting planets, but never before for a non-transiting one. Simultaneously, we aim to detect astrometric transit timing variations for the transiting super-Earth due to the fact that the hot Jupiter in the yellow plane here is just wobbling the star back and forth. So the transiting planet is orbiting a moving target. The TTV signal shown here in synthetic Kepler data for a fiducial system is on the order of a few minutes. Next slide, please. I conducted a search for these non-transiting hot Jupiter candidates in Kepler systems of transiting super-Earths and found several candidates. KOI 1822 is presented in the paper, but it's just one of our candidates. And if the non-transiting hot Jupiter is there, it should be easily RV confirmable with just a few radial velocity points. So we've been following up our candidates on the Automated Planet Finder telescope. And KOI 1822 is actually a false positive, but actually just last week we had data came down that looks particularly promising for one of our candidates. So my poster is actually on a different project, but come talk to me at my poster if you'd like to hear more about that particular candidate and this project. Thank you.
Good afternoon. My name is Tarun Sajjava. I'm from India, working on a computational astrophysics in Thapar University, Patiala. By using the theory of Rochland, by using the theory of Rochland in 1949, I have developed the equation of anharmonic for polytrope model of star of index 1.5. There are two equations. These are partially differential equations that I have developed. To solve this equation, I have taken the function q1 and q2. This is called cosine Fourier series. Put this value of q1 and q2 in equation number 1.2. I have find the value of coefficient a01, a11, a21, a31, and so on. By solving the numerically technique using the Simpson 1/3 rule and RK method order 4, I solved these two equations 1.1 and 1.2. Sorry, next slide. By finding the data of these two equations, I plot the graph in Maple software and find the variation I have taken for 2 mode, 3 mode, and 4 mode. Similarly, for the equation I have generated, that is for 2 mode. Similarly, I have generated the equation for 3 mode and 4 mode. From this graph, I conclude that the radial velocity curve of polytropic star of index 1.5 is not sinusoidally. There will be some bumps that will be makes due to the 3rd mode and 4th mode. If we generate the same equation for 5 and 6, I think there will be more anharmonic equation. Thank you.
Hi everyone. My name is Fei Dai. I'm a 2nd-year graduate student at MIT, working with Professor Josh Ren. My current research centers around the K2 mission. I'm a member of the K2 Aspirant Collaboration, which is an international team of researchers from Denmark, Japan, Spain, and US. Our mission is to identify, validate, and characterize new planets using K2. Our coordinated follow-up efforts include RV mass measurements, AO imaging, photometric follow-up, and obliquity measurements. To name a few facilities we use, we have time on HARPS North, Subaru, and Magellan Telescope. Our results so far include K222b, which is a disintegrating rocky planet, the measurement of low obliquity of WASP-47b, and K234b, which is a hot Jupiter on prograde orbit, and K239b, which is a giant planet around a subgiant star. Next slide, please. My contribution within the team is the identification and vetting of planet candidates. I'm also in charge of analyzing the RV data. One of my recent work measures the mass of the inner 3 planet of WASP-47 system. My other work earlier this year reported the Doppler monitoring of 5 K2 systems, including K2-19. These results not only constrain the properties of the planet within each system, but also offer the consistency check between RV and TTV method. So if you are interested, come and see me at my poster. Thank you.
All right, thank you to all of our POP presenters. All right, so we're gonna break. If you have not signed up for a hands-on session group, remember RVs is over there, Transits is over here. Let's limit it to 10 people per group. Please do that. And don't forget to pick up a new version of or a new IP address and stuff from the registration table. And it's poster session, so the even number posters, I mean, you can look at any of them anytime, but today is, I guess, more focused on the even number posters, and on Wednesday it'll be the odd number posters if you don't want to have to stand by your poster the entire time. So, and we'll see you back at 4:30.